I was just going to ask. Any more bingos? Woo! Nice work.
Which one?
Yeah. Yeah.
Oh, thank you.
All right. I don't know.
Yeah, all right.
I believe you.
All right. Any more bingos lurking out there? No, a few more. We'll give you another 2 minutes.
It's very professor of you.
What?
That's very professor of you.
You have to count down time, otherwise people don't know what to do with themselves.
That's true. But there will be time for more prizes. I'm waiting. Still talking. Okay, we're gonna get started with the talks of astronomy on tap now. We're gonna get started. I personally would love to hear Dr. Tuttle speak. So, okay, cool. So we're gonna do trivia again after the intermission. So there will be more opportunities for prizes. So with that, I'm gonna introduce our first speaker. You already know her. It's Professor Sarah Tuttle from the University of Washington Astronomy Department. She has tenure, which in my mind makes her about as professor as you can possibly get. And Dr. Tuttle is an absolute expert on all things telescope instrumentation and many other subjects. But today she's going to be telling you about space telescopes.
Thank you. All right.
It moves around a lot.
It moves around. It's just like a very vibes-based microphone situation. Okay. So first of all, thank you for playing. I appreciate it. Did anyone have any questions, or was this self-explanatory? Are you thinking about like third careers or second careers? Yes. Do you have a question?
Can you tell us more about the emotional support cat?
It's weird that you don't know about emotional support cats. I personally have a cat who only will sit on my lap if I'm on a telecon. So that's, that's the model for the emotional support cat. But of course, your emotional support cat could come in many different shapes. So, we don't want to limit what you need to get through the challenges. If I take this microphone off, yes. Okay. Sorry, that was very oppressive. Okay, so thank you for playing. We are now going to talk about telescopes. Maybe. Great question. I may not have. No, no, I did not. That'll help. Nope, it was on. Now it's on for real? No, it's cool. Sorry, unfortunately, I can't yet use the power of my mind to change my slides. Hold on, here, you take this. I'll fix that.
I can like be the clicker.
Oh, you can be the clicker.
I can be the clicker.
Embody the clicker. Hold on, let's see if it will let us do this. Oh, stop. It let us do this before. Okay, we're just gonna do that.
Now it's on.
It's definitely on. Oh, yay! Oh, no, but it's not. Oh, it is.
No, it's on.
Okay. All right. You got two different non-existent space telescopes. We are going to live in the imaginary today, partially because usually we don't talk about how we get space telescopes. So I'd like to talk about DISCO. Some of you now possess DISCO stickers, so you are keepers of the flame. Keep up the good work. And then we're going to talk about the next proposed flagship mission for NASA called Habitable Worlds Observatory. Some of you got that sticker also. So DISCO is a project, it's a small mission explorer. This is, the way we rank them actually is just by how much they cost, because that's obviously fantastic. It's basically an 18-inch diameter meter telescope that we're using to look at intergalactic and intragalactic gas. What does that mean? I hardly know. Oh, but I will point out, this was made by our glorious graphic designer, which earned him a spot in bingo. I think actually you just have to, oh there, you just have to move over. Yeah, the problem is, yeah. I wasn't gonna sing it, but it was tempting. All right, DISCO science goals. So one of the things about small mission explorers is that really you want one thing you're studying. When we talk flagship missions, I'm sure you've seen a lot of Hubble data, you'll even see some today. Those telescopes are built to attack a lot of different problems at once. Small missions are meant to do one thing. So the one thing we're trying to do with DISCO is we're mapping the intergalactic and circumgalactic medium. Seems silly, also feels like why haven't we done it if we can only say it in one sentence? The short answer is we have to do it in the far ultraviolet. This is light that is it's so ultraviolet, it's almost in the X-ray. So these are really high energy photons. They're also very, very diffuse, so they're very hard to see. Now, you should at least get some idea of what the circumgalactic medium is. This is drawn by a student of mine at some point, Caitlin Eigel. I asked them all to do art of this. There's a figure made by an artist in Tumlinson and Peebles and Work 2017. And because the circumgalactic medium is something we have not been able to see or map particularly well, everyone just uses one drawing. So like I was just at a conference and that drawing probably showed up like 30 times. So we tried some variety. So then I got some really excellent drawings, including this scratch rainbow, which is one of my favorites. And so here at the center is a spiral galaxy. You can see that the scale is about, we're talking tens of kiloparsecs. So if you want to hold in your brain, galaxies are tens of kiloparsecs big. The circumgalactic medium is hundreds of kiloparsecs. This is gas that is actually helping to feed into the galaxy. There might be gas coming out of the galaxy into the circumgalactic medium, just sort of gas doing stuff all around the galaxy to help it make stars or to stop it from making stars. It's multi-phase, it's different temperatures, and it has different metals as well. So this is kind of messy gas. This is not pure hydrogen. This is not pure anything. And it's 10 to the 4 to 10 to the 6 Kelvin, which humorously we call warm gas and would definitely murder us. This is like not a setting you want on your mini split. To just start to think about like how do we regulate galaxies, this is a Hubble image from the antenna galaxies. It's a pair of galaxies that are merging. And there's a lot going on in this image, even though I'm sure as, Astronomy on Tap experts, you guys could do this, but I'm just going to give you the outlines. So first of all, these are the nuclei of each. There's two of them. These galaxies are merging, but right now the nuclei aren't even near each other. There's all of this dust, right? All of these streaks are dust that's part of star formation. This whole system is star bursting. It's making stars like nobody's business. Right, so we see lots of these star-forming regions and bumps and bobs. We also, though, can see this like faint gas out here. So there is gas that really doesn't have much in the way of stars that's extending past. But you might look at this and be like, Sarah, like it's a weird merging set of galaxies. Like this is not what normal galaxies look like. So maybe I'm not that interested in your weirdo gas out here at the edges. Haha, says I. This is M83. It's a totally boring, normal spiral galaxy living its boring spiral galaxy life. I know, it's glorious, Tobin. No judgment. Obviously, I'm using it. But it is not merging. It does not have any neighborly friends, pretty much, not that close. It's just hanging out. The optical disk, the part that we usually observe if we're just using our ground-based telescopes, is this really bright part. Spirally, pretty bright in this image because we're using GALX, which is no longer in operation, but it was a UV telescope. So that's why it says FUV and NUV. And the FUV and NUV are really looking at things like hot stars. You can see there's definitely, outside of the disk, we have like some extended arm splidgy bits, right? They're not super well formed, but we can see them. These are stars and star-forming regions. But then we go over to this image. So this has the GALX images underneath, and then it has the VLA, the Very Large Array. You are familiar with the VLA if you saw Contact or took my observing class. And so the VLA is measuring radio. So this is gas that is either kind of the precursor for star formation and sometimes what gets left over. You can see that this gas is super extended compared to the kind of standard disk. And so this is the image I want you to hold in your head when we think about galaxy evolution. This is not the circumgalactic medium, and it's kind of embedded in the circumgalactic and the intergalactic medium. We sometimes call it the cosmic web, so it's kind of the stringy leftovers from galaxy formation over the history of the universe. So you can imagine gas kind of feeding into this whole system. Now, if you like arrows, you know, we all have different preferences for learning. This is, frankly, a bonkers diagram, but I will run you through it really fast. This is star formation. Sometimes in like the stellar lifetime, things happen with stars that eject material, sometimes away from the star-forming region, but sometimes out of the galaxy. So, for example, we make stars. Sometimes they blow up. When they blow up, especially if a lot of them do it at once, it shoots material out of the galaxy. So this secondary loop is material coming out of the galaxy and into the galaxy. So we're like material is constantly being moved around, gas is moving around, but it's really hard to measure because, again, often diffuse. These outflows we measure. We can see them. We can see like starbursting galaxies edge on that shoot stuff out. These inflows are absolute monsters. We just act like this works because if this doesn't happen, galaxies don't make any sense. But we do not have the evidence we really want for these kind of inflows. If you like daintier things that are hand-drawn, these are some of the physical processes that we're interested in. So, for example, fountains, sometimes stuff explodes, it goes flue, and then it crashes back down into the disk. So it might grab some gas from out here. We have cold and hot mode accretion. That's just different ways of gas coming from way far away and flying into the galaxy. When I was in graduate school, this cold mode accretion was really popular, and we all like built instruments to look for it, and then it turned out it was a mistake in the code. They don't really talk about that, but if you like get them at conferences and give them a beer, they're like, yeah, sorry about that. It's cool, it was just my PhD. And sometimes we have coronal precipitation. So if you have like a big hot cloud of gas, some of it will cool and then fall into the galaxy. So we want to understand what's important and really what dictates these different processes and when they operate. As I mentioned, so simulations are what we know about this gas primarily. And so this is an example from a simulation, this is a carbon line, this is some oxygen, from redshift 0, that's now, or redshift 1, which is back in time a ways, towards like high star forming in our universe. Now, looking at these boxes, do you feel like the circumgalactic medium is chonky or smooth? You can yell it out, you don't get in trouble here. It's chonky, right? So historically, when we thought about galaxies, we thought things were smooth. But the more work that we do and the more we measure, and the simulations, it becomes clear that we are looking for something with kind of a funky morphology that is likely chunky and leaving, it's been impacted by a lot of different things going on with the gas, right? This is cool and also in some ways harder to find. But now we can say we want to, with DISCO, try to actually find this gas and measure it emitting. We've not been able to do that in sort of these large-scale ways ever. Okay, so you might ask, Sarah, why did you spend the last year designing a whole telescope, recruiting an international team, and then preparing to put in a proposal that got canceled at the last minute? And the answer is because nothing that exists can do this work. So there's a few different aspects that are huge advantages with the SMEX platform. One of them is because we're focused on a very local problem, we can take really long exposures. So we can look at for like 100 hours, right? 200 hours at one galaxy to find something around it that's really faint. If I put in a proposal to Hubble and I'm like, I need 200 hours to stare at this one galaxy, I promise you it will be fine, they will have a good laugh before they say no, right? They'll just be like, that's delightful. No, there's still people like, climbing over each other to get Hubble time. You cannot have all of the time. But with DISCO, it's all it's going to do. So we can have a slightly smaller telescope, but we can just use it to do the one thing. The other part that's exciting is that there have been really significant, even in my career lifetime, so in the last like 20 years, there have been huge improvements in the technology that we use in the far ultraviolet. So now we can do these really hard things. We know how to do it. We've done testing on rockets, we've done testing on balloons, and even small CubeSats. We're ready to scale it up. And extra exciting is that we're able to do this testing now to make way for the next big telescope, for the Habitable Worlds Observatory. So things like DISCO are going to be precursors to HWO. Apparently pointing continues to be my challenge. There we go. Okay, I know it's not your fault. Okay, so Habitable Worlds Observatory is a proposed telescope that right now is being planned and worked on by many astrophysicists and organized by NASA. This image is a drawing, but there are a number of example, what are they calling them? EACs. I forget what these, early analytical cases, early analytical cases. So there are different telescopes and different instruments to figure out like, what can we build, what will match the science we want to do, and can we fit it in a rocket? These are all important things. So here's the thing to know. It's called Habitable Worlds Observatory. That feels very obvious. The scientific goals are explore 100 habitable zones and find 25 exo-Earths and do transformational astrophysics. There is not a category of astrophysics called transformational astrophysics. It's like only do the good stuff, okay? So I'm going to just explain briefly habitable zone and exo-Earth stuff, but I also want to point out these different spectra here, the albedos of different Earths. So when we say we're looking for exo-Earths, it doesn't mean that we are looking for exo-Earths at the same point in their evolution as we are. So a big part of the work is understanding what happens to the atmosphere, for example, at different times for planets like Earth, so we can look for them, so we can check their spectra and see if they look like we think Earth looked a long time ago. So here we have both the Archean and the Proterozoic Earth, right? But we obviously, if you kind of just look at the shape, it's not totally different, but they are definitely different parts. Nope, too far. Okay, so in its most simple, people have also called the habitable zone the Goldilocks zone, right? If you are too close to a star, it's too hot. Often we get tidally locked. You sort of burn down to rock. It's not great. You don't want to live there. If you're too far away, you're too cold, right? It is also dependent on a lot of different characteristics of the system. And when we talk about the habitable zone, we are talking about life kind of like us. Obviously, if something is wildly different and the way that life has found its way to evolve, that might mean that that habitable zone is different. But when we talk about it, we're talking about like carbon-based life form, some water basic stuff. It's like, maybe. Come on, buddy. Thank you. Okay, I just wanted to show this because I think it's useful to kind of scale. Different stars are going to have different habitable zones because they are different sizes, they have different lifetimes, they are different temperatures. So you might get much closer, your habitable zone might be closer on an M dwarf. We are a G star, right? And so we have kind of a little more room here. But also the lifetime of our sun is much shorter than, say, what's going on with an M dwarf. You also want to do some thinking about planning. So the way that we're going to detect exoplanets is using a coronagraph. That instrument covers up the star, and that allows you to see the planets, which are much, much fainter. But of course, if you cover up the star and a planet is really close to it, like say, internal planets for M dwarfs, you're not going to see them because you have also covered them up, right? So there's some trade-offs about picking stellar targets to be able to actually make detections. Okay, don't panic and don't read this slide. Mostly it's for me because it made me laugh. So this is habitable worlds. You can see these are the living world topics. These are the solar system topics. These are the growth of galaxies, and these are evolution of elements. So there's a huge number of questions that are being asked that we think that HWO can answer. It's very exciting. And some of them make me laugh because that's me, because I started reading this and I had not read all the science cases, even though I've been working on it. And then I read Birth Cries and Swan Songs of Habitable Worlds. Someone worked hard on that title, and I am proud of them. So this is kind of the transformational astrophysics. So the reason I want you to see this is that when we design an instrument, we have to balance the needs of these different sets of questions, right? Because it really is not just looking at exoplanets. But actually, it turns out you can't just have one instrument to look at exoplanets anyway. So I'm so bad at buttons, it's shocking. Okay, we're gonna skip that. So 2 instruments will probably be on this mission. Don't put this in a newspaper because they haven't decided yet and I'll get in trouble. One of them will be this coronagraph that is looking to detect exoplanets. That's its whole job. And one will probably be a spectrograph. Spectrographs make rainbows, right? So spectrographs just take the light, split it up, and you can see all different physics. You can see material, you can see kinematics, how stuff is moving. So having a spectrograph helps us understand the physics of what we're looking at. The important things for this spectrograph is that we really want to push down its FUV limit to 100 nanometers. Historically, we did not do so because we couldn't do it. The technology would not allow it. It was very hard. There have been some incredible advances, I will show you in a minute, that make it possible. And the thing that makes everyone at NASA who's working on this, because they work hard and it's hard, now it turns, rude. So this part, there was a survey. So many spectrographs are just long slits, light goes through, you get a rainbow. If you have a big galaxy, it doesn't matter, it just takes one spectrum. If you have a tiny star, same. So if you have lots of objects, you have to do them one at a time. It's slow and terrible. Nobody likes that. It takes forever. We have some great technology now, including something called an integral field unit, as well as multi-object spectrographs that mean we can actually do lots of objects at one time. And you'll be shocked to hear that every scientist that got asked wants that. You should see, the instrumentalists at Goddard are just like, why? And it was like, you knew they were gonna, you put it on JWST, like of course they were gonna ask. It's like telling people they don't want automatic windows. Anyway, so we thought we'd have to fight really hard for this, but then the entire scientific community was like, yes, please. Great, let's do that. The only rule, and this is the funniest rule, is that the UV spectrograph is not allowed to mess up the coronagraph because you have to detect the exoplanets. That's like the baseline. And the reason that's a little tricky is because light comes from the sky and it goes into a telescope, and then you send it to the instruments to do work. However, it has to come through the telescope. So if we want a UV spectrograph that is super duper blue, we have to coat all of those optics in the telescope with something that's super duper blue. And there is, a chance that that could mess up the coronagraph. So there has to be coordination between everyone so both of the instruments are able to function as designed. All right, an exciting thing, when we started doing this, I was very excited about you know, galaxies because they're cool. But I have been converted to the exoplanet way. And what was exciting to learn, of course, was that it turns out you need a spectrograph, especially in the UV, to characterize your exoplanets. Detecting them is cool, it's important, and then we need to know about them, and a spectrograph is the way we do that. In particular, it turns out that in the ultraviolet, we measure a lot of photochemistry that tells us what is going on in an exoplanet atmosphere, right? What different materials are there, what energy is being emitted, what's being absorbed. So we really need this kind of broad UV spectrograph to be able to make these measurements to confirm habitability on planets. Thank you. Oh no. Last, if we're doing this, the science case I grabbed was our circumgalactic medium. And I just wanted to show you that, you know, different molecules are emitting in different wavelengths. And the thing that kills us is a lot of the things we care about in the intergalactic and circumgalactic medium, they're only observable from the ground at really high redshift. And high redshift, things are pretty far away. If things are faint, it's hard to see them. So by moving into space, we're able to see a much broader range, and stuff comes closer to us. We're able to actually detect them. Oh, yes, great. OK, just a few. So I'm just going to flip through a few slides. I want you to know that these are exciting technologies that are being developed and that we need developed to be able to keep moving. So for example, with virus, that was the last time I was here. With DISCO, we need something that reflects light in the ultraviolet really well. I built a spectrograph a long time ago for a balloon, and this line maxed out at about 30%. So that meant 30% of the photons that hit that one surface would continue on, right? It's terrible, boo. It was the best we could do. The same lab, now many years later, has developed a bunch of coatings, but in particular this coating, which is up at like 90% in the far ultraviolet. Now, obviously we're at a brewery and there will be no quizzes, except you know when there are. But 90% is a lot better than 30%, and it means you can actually like look at stuff. Highly recommend. So this has been developed at Goddard Space Flight Center. This is a bunch of different CCD technologies. This group has coatings that have been used atomic layer deposition to put actual filters. So like this, if you have ever looked at silicon chips, looks kind of the right color for silicon chips. The other ones have these layers that have been deposited to allow us to filter light in different ways, which is exciting. So we've been doing a lot of development to improve the performance of many different kinds of detectors to allow us to, again, get better measurements, work faster, that kind of thing. Every time. And this, just because, you know, who doesn't love the shenanigans? This is, these are called microshutters. This is one technology that enables multi-object spectroscopy. So if you look down in this corner, it looks like there's, I don't know, little sorting bins or something. These tiny bins are actuated with electricity. You can pick which ones open, select which part of the sky brings in light. So maybe you have a whole bunch of stars, maybe you have multiple galaxies. You get to pick. Once you've selected them, that goes through the instrument and makes these spectra. In this instance, all the spectra are the same because it's a calibration lamp so this is like in lab, not in space. But you can see it allows you to sort of look at many different objects instead of what we would traditionally see, which is just one long line. You know, it's not perfect. These ones didn't open, boo. But you know, it's exciting. So this was developed at Space Telescope as well as at Johns Hopkins for JWST. So this is flying in space. We've used it in a bunch of different formats, and it's being developed for UV. So that is super exciting. Should check my time. Oh, good, fine. All right. However, now that we handed out stickers and some of them were sparkly and we were super excited, this is NASA's budget requests from 1961, a year you might recognize. Something exciting happened then, to now. So this is Apollo. This is, I don't know, JWST is like forever. And this is what NASA is currently operating with. NASA has made the choice to use the presidential budget request for 2026 as their current budget, and it is absolutely devastating. if you are someone who likes histograms, you can see it's not that NASA never gets budget cuts. I mean, like no one thought we were going to Apollo again, right? Like that was cool, but no. So you can see, right? Some years we get some percentage cuts, maybe 10, 5%. But this year it's a lot, and it was already not good, right? So we've kind of gone from everyone's basically holding their breath to like, oops, there's nothing to do. You can also see, I don't expect everyone to hold like NASA's org chart in their head, but if you do, congratulations, it's really big. The thing where we work primarily in the Science Mission Directorate. SMD has 4 branches. It has astrophysics, we have planetary, we have earth sciences, and heliophysics. This will be relevant in a second. There's a picture. We're looking at almost 50% cuts in science. And science operations, we do get a little bump in deep space. And STEM, so education and outreach, has been zeroed out. So it's kind of grim. Yeah, I don't love it. You should know. Yep. This is, I actually really love this poster. I love it more when we're not canceling missions, but you know, even now. So these are solar system missions. This is the Earth. These are heliophysics, and this is astrophysics. Any mission here that is bolded is a mission that hasn't flown yet. So it's been selected, it's probably had funding, but it hasn't flown yet. And then any mission that has a red dot next to it is canceled. So that's not great. These are all things that are working, right? Like these are missions that are up, they're taking data, people are working on it. It does also include one of our flagships, Chandra. It includes UVEX, which is our most recent MIDEX selection, which is also a UV survey telescope. And LISA, if you love gravitational waves, you love LISA. It's a European-led mission, so there's some possibility that maybe things still happen, some, but unclear. Oh, good. And this was just to like, I think one of the things for me that has been the hardest is, you know, people work really hard on these, right? Like with everything. No one shows up to build a space mission because like for the money. I mean, you know, everyone loves having enough to eat and pay their mortgage, but like no one shows up to do this because they're buying their 16th house. So you can just see here, Chandra's been absolutely knocking it out of the park with the X-ray since 1999. Like I was, yeah, we won't talk about where I was then, but I was not building Chandra. And so you can see, you know, these are missions that have been up for many years. They have taken a combined 180 years to build. Obviously, that's not people time, right? That's just, it took X number of years to build this thing with all these people doing it. And something like $12 billion of investment. So it would be a real loss to turn these things off. I would love to tell you that we could like, I don't know, make some phone calls or like send in a postcard and it would like magically get fixed. I believe we have tragically passed that window. Here we go. Oh, too far. I was too successful with my buttons. So, you know, I think as scientists, we do our best to really think about the evidence in front of us. And the evidence in front of us right now is we have moved all the way down the path, and we have a government that has embraced fascism. Our CDC director got fake fired on Twitter today and is trying to hold on to her job. One of our governors at the FDC also. So, you know, we're not in a place where things are stable. Now, I, for one, obviously, will fight day and night for space telescopes because I love them with my whole heart. But I think we also have to think about the large-scale impacts. We're seeing them in our schools. We're seeing them at the university for sure, right? Again, NIH cuts have all gone through. Cuts for Medicare will likely damage our medical systems, including UW Medicine. I happen to know that doctors have been told that they will receive 30% salary cuts in preparation for that, with like no path forward. So I think we really need to engage, and for all of us it will be different, right? I might yell at people at NASA because that's who I can yell at. But we all will find pathways that we really make sure that we point out when these things are happening. We'll lose some stuff, but hopefully we can fight hard and, you know, keep the things that are closest to our hearts. These days, it's a lot of things like fighting for LGBTQ rights, showing up for immigrants who are being grabbed off the street while they're working, So, you know, those things we should prioritize. And then if we have a little energy in the tank, maybe we can build some space telescopes too. All right. The cool thing is that people are stronger than fascism. So I wanted to share with you this. I thought this was very sweet. This is a sampler that was embroidered. It's in the Victoria and Albert Museum. Part of why I think it's charming is because I very much imagine like a very saucy 10-year-old child who's like, you want me to embroider? Fine. And then embroidered the solar system. It has lots of fun things, but my favorite thing is that it was made in 1811, and 1811, there was the Great Comet of 1811. It was the most visible in the sky to the naked eye comet until Hale-Bopp, many 150 years later. So whoever has sewn this has sewn the orbit of the comet, and look, there's a little comet with its tail. Very detail-oriented. We would recruit this person. So that made me happy, and then I wanted to leave you with my favorite part. This is the Roman Space Telescope. Roman is the next thing that we're going to fly next year. Roman is basically done. We're going to go with, don't tell Goddard Space Flight people that I said that, but it's basically done. So this is it fairly assembled. They take it apart and put it back together again to test different pieces. It can't all fit in all of the chambers, and so they go through cycles of testing and then fix stuff and put it back together. And then an airplane lands on us. So Goddard is kind of has been one of the central space flight centers from Apollo. Like you can walk through the hallways and find like weird test apparatuses that are like larger than this whole space. And it's like, what was this for? It was like, oh, we put, you know, this part of Apollo in it and just spun it around and waited till it broke. That is not my job, tragically. So there's a lot of really exciting things at Goddard. Unfortunately, they have been targeted, and many people have either been forced to retire or have been fired. So we have lost, as we talk about the Habitable Worlds Observatory, which we're so excited about, we've lost something like 40% of our expertise because they happen to be in a blue state. So on that note, I will show you my favorite telescope that I'm never allowed to build. This is both a bad use of books and also feels like a health and safety OSHA situation. But I do love it. So thank you very much. Thank you for playing bingo with me. And I hope you have a good rest of your night. Oh, I can take questions. I thought I might have taken over my questions. Who has questions? Yeah, okay, just in case. Who knows? Maybe I'll have used it by then. Yes.
Magnetic core being vertical piece of light box. Is there any way to identify that on exoplanets?
Not yet. Not yet. There's definitely, so, you know, this is like maybe it's the running astronomical joke, like polarimeters can do anything. But we don't have anything that can detect that kind of signal right now at the distances that we are. Yeah, but that would, you know. Any other questions? None? I told you so many stories. I appreciate that you believe them. It's very brave. All right. Thank you so much.
So at this point, we're going to take our 5 to 10 minute break. When we come back, we will do trivia, and that will be followed by the final talk of the evening. You should all have trivia sheets, but if you got your player or whatever, you decide you want to play trivia and you don't have one, you can come get a trivia sheet from us during the intermission. Thanks. during the second talk. Okay, let's get started. last talk. Again, if you have trivia sheets and you played trivia, please bring that up to us. We're going to grade them right now and then announce the winners at the end. So at this time, it is my pleasure.
Hold on, give me 2 seconds.
Technical difficulties again. 1 second. How's everyone's night going? That's good. Me too. That's why I usually respond to that question too.
Dickerson's guess.
How's it going in terms of the laptop?
What are you trying to do?
I was using my hotspot. My phone died.
Why do you need to be on this?
Because I can't access my slides.
It's probably just not, it's not mirroring your display. It seems like your slides were just fine.
Okay. No, it went offline for a second. Just move the tab over.
So, yeah, you could do that if it's on extend screen.
Or I can just mirror. Sorry. That's smarter.
There we go.
All right, we're good to go. All right, so at this time, it's now my pleasure to welcome the second speaker of the evening, Aishan. Aishan is a recent graduate of the University of Washington Astronomy Department, and they have secured an elusive grad school position next fall. It was very hard to get this year, so congratulations. And they are going to be telling us about more light than heat.
Hello, my name's Ashan. This year I am a graduate of the UW Astro program, class of 24. This year I've been doing a post-bac at the department while I've been trying to get into grad schools. So this talk is going to mostly focus on massive. Can I lower this mic a bit?
You can, you
Okay, there we go.
You can just take it off of the stand.
That might be easier.
That's what the stair has to do.
Okay. This talk is about massive stars. This talk is arranged in a little bit of a weird way. It's a bit of an experiment. It's kind of a 5-in-1. I'm going to talk about 5 different ways I have attempted to study massive stars, what I've learned from each of them, and how that kind of fits into the big picture, puzzling together how massive stars work. This first project starts in 2020 when I was starting out at UW Astro and was in a program called PREMAP, which is a program that is supposed to lift up underrepresented groups in STEM by giving them early access to research and the tools they need to succeed in astronomy. I worked with my PREMAP partner, Bilal Smith, and 3 mentors. In that project, we started to work on massive stars. I was already really excited about red supergiants and massive stars when I came into UW, but let's define what a massive star is. The trivia is actually wrong. It's not greater than 25 solar masses. It's stars that are greater than 8 solar masses. So massive stars are any star that's greater than 8 solar masses. So they can be up to 100 solar masses, though, and they have very interesting lives and deaths. There are 2 ranges of massive stars we care about, the ones that are 8 to 25 solar masses and the ones that are greater than 25 solar masses. The main difference between those 2 is how they end up evolving. Massive star evolution is really weird. Most massive stars tend to start out as main sequence OB stars, and they usually end up being red supergiants, but what happens in between is really weird. Most stars will evolve from hot to cold, so they'll go from blue to red. Massive stars can sometimes evolve backwards. We might talk about that more later. But what's really interesting about massive stars is how they end their lives. If a massive star is 8 to 25 solar masses, it'll typically end its life as a neutron star. If it's greater than 25 solar masses, it'll typically end its life as a black hole. The average massive star towards the end stages of the typical 25 solar mass massive star will spend most of its life fusing hydrogen to helium. then helium into carbon, carbon to oxygen for about 600 years, oxygen to silicon fusion lasts 6 months, silicon to iron fusion lasts about 1 day, and then the second enough iron builds up in the core that the star tries and fails to fuse iron, because iron is at this weird tipping point where every element lighter than iron, you get energy back as you try to fuse it. Every element heavier than iron, you get energy back when you try to split it. But with iron, you lose energy either way. So in a fraction of the second, the star's core will collapse, and you get this. This is a core collapse supernova. It's the violent end that awaits most massive stars. If this star was 25 solar masses, so it's right at the edge. So if it was just below, it would almost definitely turn into a neutron star. If it was just above, there would be enough gravity and forces at play here that it would collapse all the way down to a black hole. This is probably the poster child of massive stars, Betelgeuse. Betelgeuse is a star that's very easily observable. If you can find Orion, you can find Betelgeuse on one of its shoulders. Betelgeuse, this is a time lapse of Betelgeuse over a course of about 18 months. You can see something very interesting happening with this star. You can kind of see it's almost bubbling and boiling. It kind of looks like your stovetop when you've been boiling water up to its boiling point. What you're kind of seeing is convection cells in this massive star. And this convection cell is an effect that happens when you get to these late stages of massive stars. You can actually kind of trace it out with the star's variability. So this is a light curve. This is the star's variability over time. On the y-axis and the vertical axis, you have brightness. On the x-axis, you have time. You can see 2020, about when I started college, there was a very big mysterious dip. There was a lot of speculation, and it was very exciting to come into college at the time and have a lot of speculation about what caused Betelgeuse's great dimming. As it turned out, it was just dust. It's kind of boring, but dust occluded the star for a bit, and that caused the great dimming of 2020. But this is not the only way we can study a light curve of a star. This is great data. We have brightness over time, but we can do math to it. I'm not going to bore you with the math. I'm just going to show you some few plots. But one thing we can do is take something called a periodigram. And using it from a periodigram, we can extract different features, such as amplitude, time scale, which are some of the features we can extract from a light curve. These can help us featureize a star's variability and extract physical parameters. If any can see a bump around 10 to the 0, that's actually, in that periodigram, that's actually one of the pieces of evidence we have for Beetle Buddy, Betelgeuse's companion star. Yes, we named the companion star of Betelgeuse Beetle Buddy, and I think that's incredibly cute. Right. Yeah, so amplitude, time scale. I'm just going to skip past this. Okay, takeaways from this initial project for me and for all of you. Massive stars are cool. Massive stars do fun things. Cool massive stars, so the red ones, are very cool. We can measure a star's brightness over time. This is called a light curve. We can use math to extract features from a light curve. These features can inform physical properties of the star. In this case, we were trying to use it to describe the convection going on in Betelgeuse's atmosphere. So, part 2. Photometric classification of evolved massive stars using spectroscopy. I continued working with the same 3 mentors, a grad student, Trevor Dorn-Wallenstein, Professor Emily Levesque, and Professor James Davenport. You don't get too far into talking about the history of stellar astronomy without talking about these people. This is the Harvard computing group of the late 19th century and early 20th century. Featured is Annie Jump Cannon, Henrietta Swan Leavitt, and the entire Harvard computing group. These were a group of women who, for the absurd logic of patriarchy of the 20th century, were not given the title of scientists, but were called computers. They were called the Harvard Computing Group. And what they did was one of the many accomplishments of this group was coming up with the classification system of stars that we use now. prior to this, we used basically an alphabetical system. And what Annie Jump Cannon figured out was this system didn't make the most sense for actually showing the progression of stars. So what Annie Jump Cannon did was merge a bunch of these categories, reorder them in order of the progression of chemical lines. And we end up with O, B, A, F, G, K, M, which is a wonderful series of letters to try to remember. There are a couple of mnemonic devices. The one that Annie Jump Cannon came up with was "Oh, be a fine guy, kiss me." I prefer old bread and food gets kind of moldy. But the main takeaway is whatever mnemonic device you use to remember these letters is OBA stars are hot and blue, F and G stars are in the middle, and K and M stars are cold and red. I do regularly annoy all my art friends by constantly reminding them that red is cold and blue is warm. But yeah. About the same time, like within a few years, Hertzsprung and Russell published this diagram, which plots luminosity on the y-axis and temperature on the x-axis. When Jump Cannon created the OBFJKM system, she was not completely aware that what she'd done was pre-discovered this diagram in a way, where the order of stars as they appear out in temperature follows the order of the chemical progression. So to talk about this a little bit more, we need to understand not just massive star evolution, but normal or low mass star evolution. Low mass stars spend most of their time on the main sequence, which is this thing, this main line going down. They will start somewhere on here. They'll spend most of their lives there. The sun is right there with the G stars. It spent 5 billion years there. It'll probably spend another 5 billion years before it runs out of hydrogen, moves up to the red giants, move around a little bit before eventually going all the way around and ending up as a white dwarf. That's the progression most sun-like stars will take. Some sun-like stars will end their lives as a planetary nebula. Most sun-like stars will end their lives as a white dwarf. As a reminder, massive stars just as a quick refresher, massive stars are a little bit weirder. Red supergiants are all the way up in that corner where they're very red and very bright, almost as if they have more light than heat. I wonder where my talk title came from. So how do we study these stars? We talked about light curves, which is a form of something called photometry. Light curves are actually something called time domain photometry, so photometry conducted over time. Another tool that we have is spectroscopy, which is where we look at the chemical signatures of different stars. This is actually what Annie Jump Cannon was looking at when she figured out this progression. You want to see this very neat progression as we go from O stars at the top to M stars at the bottom. There's a very systematic progression with the chemical signatures of these stars. You can see that even the N stars have a very telltale look where they kind of have lights taken out. All of these discoveries at the turn of the, I think it was 1920s, was Cecilia K. Koposhkin was a PhD student working with Jump Cannon to discover the fact that our previous assumption at the time, which was that stars have the same chemical abundances as planets, was in fact wrong. Stars are mostly composed of hydrogen and helium because they will spend most of their life using hydrogen into helium and are mostly composed of these. She wrote this up in her PhD thesis, which is now also sold as a book with the line, one of the most brilliant PhD theses ever written. Because it's a work that established what our current understanding of stars, the understanding that stars are mostly made of hydrogen and helium, and flew in the face of what physics and astronomy thought at the time. So much so that there had to be a little disclaimer in the thesis saying that the result couldn't possibly be true. And even when it was proven true, A. McCaughton was denied credit for a few years by her advisor. Okay. Going back to the present, this is a lot more washed out of the stuff than I was expecting. This is an attempt. When you're classifying stars by spectroscopy, you have to do it usually one by one, which is very exciting. Anytime there's an opportunity to do a kind of survey that allows us to look at multiple star spectra at once. But it is very tedious to classify stars the way John Cannon and David Ashton were doing it. So what if you could instead not use spectroscopy, but instead rely on photometry like light curves, which are easier to take, and then throw machine learning at it? Well, as it turns out, at least in 2021, it wasn't that easy to just get the classifications directly out there. But what we could do is we could break them into hot stars, so OBA stars, cool stars, FGKM stars, EM stars, stars that are having a weird emission feature and behaving weirdly, and contaminant low mass stars. So we could break them, at least for massive stars, we could break them into 3 categories and filter out some of the contaminants. And we could do this fairly well. The way to read this table is when you're looking at the percentages, the bluer the diagonal, the better your machine learning algorithm. This one on the left is more showing the numbers in each one. So you can kind of see, oh, there are way more hot stars in this example than cool stars. What I was tasked with doing was, okay, this works for the stars we have labels for. This works for the stars we've already classified. What if we turn this machine learning algorithm on stars that have never been classified before? Would it still work? Is there some bias in the algorithm, or can we apply this to new data sets? We turned to Apache Point Observatory. This is not actually the telescope and Apache Point I used. It's just a very nice picture. The big 3.5-meter telescope is the one I used. And this is the methodology that we followed. So stars, the OBA, FGKM star categories, actually each have set 10 subtypes. We're not going to worry about those. We're just going to worry about the letters. And I'm going to speed run classifying a star in real time. So first thing we look for is, does it have those big flights that are missing, like the M stars? No, it does not. It's not an M star. Then we look for hydrogen lines. Does it have hydrogen lines? Yes, if it has strong hydrogen lines, that means it's probably a hot star. So the final check, does it have any strong calcium lines? The calcium lines are no stronger than the background signal. So no calcium. Is there helium present? Yes. Okay, so now we know that it's either a O, B, or A star, and we have to determine which one. So helium present is not an A star. No helium-2, which is ionized helium, or helium that has is energized. So we know there's no, we see that there's helium-1 present, but there's no helium-2 present, so we end up with a B star. Okay. We also have this weird feature. And in investigating, we can actually determine the shape of the star from that feature, because that feature is an emission feature of a PE star. And by the shape of that feature, you can actually determine that this is a star with a disk. And you can determine the angle at which you're viewing the disk from the shape of this emission feature. So, from problem 2, you know that spectroscopy allows us to trace our evolutionary state, so OBA, FGKM. We know spectroscopy allows us to figure out many things about a star, other than we just talked about the spectral type of the star, other than just determining whether the star has a weird feature like this. We can also determine a star's luminosity, its rotational speed, its metallicity, even the star's surface gravity. Spectroscopy allows us to identify weird and interesting stars like that VE star we just talked about. And it's hard to do at scale compared to photometry, which is taking light projected light curve. Machine learning can use time domain photometry to broadly classify massive stars. There have been multiple follow-up studies that have attempted similar things and have shown that this is a successful technique. I'm using various spectra. I was able to classify 15 different stars manually, but 15 is not a lot, especially when we have like 40 billion stars in the Milky Way. 15 is kind of slow going. So, I wanted to investigate what this variability looks like in hot massive stars, the blue stars, the OBA stars, in Gaia and ZTF. We've already talked about what variability is. That's the change in brightness over time. We talked about what hot means, the blue OBA stars. We talked about what massive stars are, those are stars that are greater than 8 solar masses. So this is a light curve of a cold massive star. This is Betelgeuse light curve. And most of Betelgeuse variability is what we call intrinsic. It's internal to the star. Not all variability is intrinsic. Some variability is extrinsic to the star. Something other than the star is affecting what we're seeing in the light curve. For example, a planet transiting in front of the star. You don't have to be able to read this. This is just a diagram showing the different types of variable stars and how they're all connected. You can see the green stars are all the different types of pulsating stars. The kind of pinkish magenta stars are the ones that are cataclysmic variables. You have, we also have asteroids and AGN which are not stars, but there are other types of things like cause variability when you look at the night sky. We have extrinsic examples like something eclipsing it, like a planetary transit, rotation on microlens. This is just to show all the different types of variable stars astronomers have to think about when they're looking at variability in the night sky. I wanted to use Palmer Observatory as a key transit facility, which is a survey telescope that has been surveying the night sky for nearly a decade. And the Gaia mission just completed its 10-year survey and was retired this year. And try to find interesting stars to find light curve stuff and try to understand what are the different types of variable stars that exist in the blue. What are the interesting types of blue variable stars? So some stars you'll notice have very chaotic and sporadic. There's no just looking at the light curve, you wouldn't notice. You wouldn't be able to tell that something's going on. You would notice that there's some gaps in the light curve as well. Those tend to be when the telescope is unable to see the star because the star is on the wrong side of the planet, because you move through space. And some stars have very obvious variability. So much so that if you are able to find the period of that star, so how frequently the time it takes between its peaks, and then you fold it by the amount of time, you can actually see a very clear pattern in the variability. This pattern, which Cepheid variables have, because they're very regular pulsating stars, is what Henrietta Swan-Leavitt, one of the scientists in her computing group, used to be able to figure out something called Leavitt's law, which is the fact that for certain types of stars, like Cepheids, if you know their period, you can also extrapolate their luminosity. And if you know the star's luminosity, you know how bright it is, so you can also figure out how far away it is. I also, with this data set, did some follow-up experiments with smaller cadence observatories. I used ArcSat when I was in Sarah Tuttle's class to look at, try to look at stars that seem interesting in Gaia, that we can have very complete light curves of. And then at Monash Ridge Observatory, I tried to compare the short cadence light curve of various stars. I didn't explain what cadence is. Cadence is how frequently you're looking at a star. So a high cadence star, if you're looking at a star with high cadence, like we were at MRO, the National Ridge Observatory, we might be taking multiple samples a night. With a low cadence observatory like a big survey telescope, they might only look at a star once in a week, maybe not visit more than once a month, so you don't get as frequent visits to the star. So high cadence observing is good for when you want a star that has something happening on a very short time scale. Like you're expecting it to pulsate on a scale of maybe once a day or once every couple of days. If a star is pulsating very slowly, you don't really need high cadence of observations. You're okay to use just a survey that's only going to look every so often. The survey I'm really excited for, most half the astronomy community is really excited for, is the Legacy Survey of Space and Time conducted by the Verity Rubin Observatory. I think the last AOT was about Rubin, right? I'm not going to bore you with more Rubin facts, but Rubin is going to generate like 6 petabytes of data every year for 10 years. So we're going to have a 60 petabyte survey covering the entire southern hemisphere sky, a little bits of the northern hemisphere that's close to the equator. It's going to be a tremendous amount of data. We're going to have covered in 6 different bands, 6 different colors. So we're going to be able to do a lot with this. It's going to be very exciting. When that data eventually gets released, that'll be very exciting. So, surveys are good. Surveys are good for moderate to low cadence photometry. Small ground observatories are good for high cadence follow-up photometry. Rubin is a survey of space and time. It can generate a fire host of data with most notably with poor distances and no spectrum. So there's no spectrum being created by Rubin. Rubin is only taking brightness in different colors, but it's not getting a spectrum. And also for most of the survey, Rubin will not be able to generate reliable distances in the same way other missions and surveys, like for example, Gaia did. Gaia has given us some of the best distances for mapping out the Milky Way, and Rubin will not be able to, for a while, not be able to do it to the same level of detail. And blue stars have a lot of interesting variables. We talk about Cepheid, for example. But what about the red stars? Some very periodic stars can be used to figure out properties like luminosity and distance. That's what Leavitt's law is. That's what Henrietta von Leavitt worked on. What if that was not only true for Cepheids and others, for other pulsators are layers, which is also true for? But what if variability was intrinsically linked to multiple different things in a star? What if you could, for example, determine a star's surface gravity, which is directly related to the star's mass and radius, from how its variability worked? There's not a direct connection there. There's not like direct math we can use to figure that out by looking at an individual star. But maybe if we combined a bunch of different stars and had measurements for all of their surface gravities, we could somehow figure out a way to extrapolate the star's mass and radius from its variability behavior. So just to recap one more time, when astronomers talk about temperature, right, I don't know what I did with my slides. Yeah, okay. Okay, there we go. So when astronomers are talking about temperature, once again, blue means it's hot, red means it's cold. Once again, looking at the first Astronomical diagram, you can see as stars get redward, there's a very big divergence between red supergiants and main sequence stars. This is also more washed out than this is another way of looking at it. So previously we were looking at luminosity versus temperature. This is a plot I made that has surface gravity in log scale, so exponents. Surface gravity log scale versus temperature. We see a similar pattern. We're seeing that we have towards the top a bunch of giant massive stars, and along the bottom a bunch of dwarf stars. And we especially see a break around the same temperature around 5,000 Kelvin and colder, you're kind of seeing that break between the bigger stars and the smaller stars. You're seeing the same kind of break happen when you plot it with surface gravity instead of luminosity. Maybe there's something here. So I went back to LSSC data is not that fantastic. We only have the data previews. We don't have any of the main data releases yet. But ZTF is also a pretty good survey telescope. It's taken a lot of decent coverage of the sky. It has decent photometry and cadence, and it's done it in 2 different colors. It's done it in what we call the R band and the G band. So we can have a star, look at it, see what it looks like in the G band. This is a different star. I don't know why I put 2 different stars, but this is a star in the R band. So you have R and G. So you have a greenish band and a reddish band. Astronomers are terrible at acronyms. So this is an actual documented package that is available for you to use when you do timing in astronomy, and it's called FEATS. I don't know why that's what they went with. They put FEATS in their logo. But it's a feature extractor for time series. This is a real thing. This is there's published papers with this. That graph also looks terrible. Okay. Effectively, what I did was I took the time series for hundreds of thousands of stars. I extracted their features like we did in the first project where we got 4 features out of our red supergiant, except this time there are 200 something features across 2 different colors. And then try to train various machine learning models to predict them. On that graph, basically the higher up the line, the better the machine learning model. So most of them are terrible. Some of them came up on top. I tested about 50 different models. This plot is terrifying. I couldn't figure out a way to put it on a slide. I don't think I'm going to ever find a way to put this on a slide. Machine learning goes verb. It's the main takeaway from this. What this plot is on the x-axis is positive and negative correlation. So how well related is a feature compared to surface gravity? So how well, if I just look at one feature, how well does it predict the surface gravity of the star? The thing that works best in unsurprising is color, which if we go back very briefly. Okay. Makes sense. Color, as color changes, the surface gravity of the more massive stars tends to increase. So there is so it makes sense that color predicts surface gravity well. There is a bunch of other features. None of them correlate that well, but maybe put together they can. So this is once again a matrix showing how well a machine learning algorithm can predict whether a star is a dwarf or a giant star. However, in this case, the previous thing I said about the bluer your diagonal line, the better your machine learning algorithm, this is kind of where that stops working, because you can see that we have 70-ish% accuracy, so like the light blue on the giants, and then the deep blue to 90% accuracy on the dwarfs. And the second model has like 94% accuracy on the dwarfs and 85% accuracy, 95% accuracy in the giants and 85% accuracy in the dwarfs. And then when you plot like how good are you at actually predicting surface gravity, it turns out that first one was kind of just terrible and just kind of lucked out by where I made the cuts in my model. So instead, let's skip this slide. I don't know what it's on. So instead we can make a plot like this, and I now looking at like hundreds of these plots with too many machine learning models to go through. And you can kind of see on the y-axis is where the machine learning algorithm thinks the star's surface gravity is. And the x-axis is what the surface gravity of the star actually is. Massive stars, the stars that are have a lot of mass and also swollen up to a huge radius, like red supergiants, will be very low toward the bottom quarter close to the origin. Red dwarf stars, which have much smaller mass and a really small radius, will be all the way toward the top of it, if they're predicted correctly. None of the algorithms are fantastic. That's a good follow-up question for why. But the main takeaway is that there is definitely something here across algorithms. It's able to pick up some stars up by the dwarfs correctly each time, and it regularly changes behavior under surface gravity 1, which is where we expect red supergiants to be, but don't quote me on that because I still need to figure out if that's true. But there's something here. So Leavitt's law allows us to figure out the luminosity of certain types of pulsating blue stars. Potentially, machine learning can help us figure out the surface gravity of red stars. The ideal magical version of this plot would look like this. This would be a fantastic plot to be able to make. This was made accidentally when I accidentally fed it the machine learning algorithm some errors that included the distance to the stars, because once you know the distance to the star, it's really easy to tell how big a star is if you know how far away it is. This would be the magical ideal that you could achieve from variability alone. Unfortunately, it does not look like that yet. And then part 5, which is what's next. So currently, I'm still working on trying to figure out how well with ZTF data can you predict the surface gravity or mass of a star from its variability alone. In September, I'm going to be starting in grad school in Leuven, Belgium, mostly because I don't want my grad school PhD program pipeline to look like this. I'll leave it up here for a second. I'll have to read it out loud. But just as a conclusion for takeaways at the last 5 years of doing research at UW, is that massive stars are really cool. Astronomers have several tools in our arsenal to study stars. In order to properly decode stars, we need various different angles and strategies. Also, Cecilia Payne-Kokoschkin, Annie Jump-Cannon, Henrietta Swan-Leavitt, and many other historically underrepresented people in astronomy have done awesome work and are really cool and should be uplifted more. The other very cool thing is this version of the periodic table, which shows where different stars come from, different elements come from. So you have hydrogen and helium that mostly came from Big Bang fusion. You have all the ingredients for life up in the first couple rows of the periodic table, mostly coming from and being distributed by exploding massive stars. You have other types of stars filling in the rest of the table, which leads to my favorite astronomy fact of all time. We're all made of star stuff, and obligatory saying again. I also do need to thank several people and groups. This is my last talk while being a part of UW Astro. So, I need to thank my mentors. I've had 3 mentors very consistently for the last 5 years, from Jim Davenport, Emily Levesque, and Trevor Dorn-Wallenstein, who still continues to mentor me from all the way to California. I've had many wonderful professors and I've had wonderful research classes, including taking Astro 480 with Sarah Tuttle. I've had many wonderful collaborators. I've had a wonderful time working with both the Dirac Institute, which is working to discover the universe using data-driven astronomy, and the Legacy Survey of Space and Time, the Massive Stars group as well, I've had many wonderful friends. Thank you for Bruce and Matt for showing up for me today. Sigma has been a huge part of my last 3 years at UW. Sigma is sexual orientations and gender minorities in astronomy. It's a RSO that represents a committee in the American Astronomical Society here at UW. I was one of the founding members and chair. Bruce was the chair this last year. Right. Sorry, I believe I was going to say. I've also had the good fortune to be able to mentor students at UW Astro. I've worked with 2.5 students this summer, and I've been very lucky to be able to start them on their research journey and kind of pay forward all the free time that so many people have given to me to make sure that I've been successful as an astronomer at UW. Okay, sorry, I remember what's in. And Barbara's taking over as chair of Sigma in the coming year. So as a whole, I want to just thank the UW community for the time and mentorship I have received here. And that's the end of my talk, and I'm happy to take any questions.
Time for maybe one question. We're coming up on when the room is closing. Yeah.
Theoretical maximum how big a star can ever get?
Theoretical, I don't know. The most massive star we've ever measured is, I think, over 100. It's about 100 solar masses, and I think its radius stretches past Saturn's orbit.
Let's take a shot one more time.
Oh, I forgot to give you one. Okay. Okay. All right, let's give both of our speakers another round of applause for 2 really great talks. I'm going to go through the answers super duper quickly so we can all get out of here at the time the brewery closes. So first one, X-ray satellite first launched into space. Oh, I'm reading off my sorry. And yeah. Okay, the answer was B. Okay, number 2. There's 18 segments on JWST's mirror. Sun-like stars is what HWO will be observing. Black holes and neutron stars are the brightest in the X-ray. X-rays are blocked by the Earth's atmosphere. Massive stars explode as supernovae. Ishan talked to us about that a lot. Mira Ossetti, first variable star discovered. Cepheid variables have a pulsation period that relates to luminosity. Again, Ishan told us a lot about that. Betelgeuse was dimmed when a giant dust cloud blocked a part of its light. And finally, Wolf-radiant stars shed their outer layers in powerful stellar winds. Okay, we have 2 winners. So both of them got 8 answers correct. First team is, what is eggs? Good job. Good job, what is eggs? And the final winner is Sydney Anderson. Okay, so when I stop yapping, you can come up here and get a prize. But with that, our next Astronomy on Tap, don't forget, is September 24th. This is my last Astronomy on Tap as organizer. I did it. That concludes 3 years of organizing this event. Thank you. It's been a pleasure. You guys are really the best audience.